If I multiply a matrix by most vectors, the result points in a completely different direction. The vector rotates, but there exist special vectors called eigenvectors that matrix. Multiplication cannot rotate. These vectors only stretch or shrink. Today we find them. The equation is A times V equals lambda times V. A is the matrix, V is the eigenvector, and lambda is a scalar called the eigenvalue, telling us how much the vector stretches. This single equation is the foundation of PCA, Google PageRank, quantum mechanics, and the stability of every dynamical system ever studied. Picture the matrix A acting on the plane. For a generic vector U, the output A times U points in a completely different direction. The matrix has rotated it, changed both its length and its orientation. This is the normal behavior of a matrix. Most vectors get rotated. Now try the special vector V1, which has components 1 and 0. Multiply A times V1. The output is 3 times V1, exactly 3 times the original vector, in the exact same direction. No rotation, only scaling. We call this vector an eigenvector with eigenvalue 3. Every matrix has these special directions. The eigenvectors are the axes along which the transformation is purely a scaling operation. Once you find them, you understand the essential geometry of the matrix, what it stretches, what it compresses, and what it reflects. These are the natural coordinates of the transformation. The formal definition: a non-zero vector V is an eigenvector of matrix A. If there exists a scalar lambda such that A times V equals lambda times V, lambda is the corresponding eigenvalue. The vector V must be non-zero. The zero vector satisfies this trivially for any lambda. The eigenvalue lambda can be any real or complex number. If lambda equals 2, the eigenvector is stretched to twice its length. If lambda equals -1, it reverses direction. If lambda equals 0, the eigenvector is mapped to the zero vector, meaning A is singular. The sign and magnitude of lambda tell the full story of how that direction transforms. The set of all eigenvectors corresponding to a given eigenvalue lambda, together with the zero vector, forms a subspace called the eigenspace of A for lambda. This eigenspace is also the null space of A minus lambda times the identity. Every vector in this subspace is an eigenvector. A scales them all by the same factor lambda. Start from the equation A V equals lambda V. Rearrange. A V minus lambda V equals 0. Factor out V using the identity matrix. A minus lambda I, all times V, equals 0. We need non-zero V in the null space of A minus lambda I. This requires A minus lambda I to be singular. A matrix is singular exactly when its determinant equals 0. So the eigenvalues are the values of lambda that make the determinant of A minus lambda I equal to 0. This is called the characteristic equation of A. The expression det of A minus lambda I, when expanded, is a polynomial of degree n in lambda. We call it the characteristic polynomial of A. The characteristic polynomial has degree n for an n by n matrix. By the fundamental theorem of algebra, it has exactly n roots counted with multiplicity. These roots are the eigenvalues. For a 2 by 2 matrix, we get a degree 2 polynomial with at most 2 eigenvalues. Finding eigenvalues means factoring this polynomial and reading off the roots. Find the eigenvalues of matrix A with first row 3, 1 and second row 0, 2. Step 1. Form A minus lambda times the identity matrix. We subtract lambda from each diagonal entry, leaving the off-diagonal entries unchanged. A minus lambda I has first row 3 minus lambda 1 and second row 0, 2 minus lambda. The determinant of this 2 by 2 matrix is the product of the diagonal entries, minus the product of the off-diagonal entries. That gives 3 minus lambda times 2 minus lambda, minus 1 times 0. Expanding. Lambda squared minus 5 lambda plus 6. Set the characteristic polynomial equal to 0. Lambda squared minus 5 lambda plus 6 equals 0. Factor. We need two numbers that multiply to 6 and sum to -5. Those are -3 and -2. The factored form is lambda minus 3 times lambda minus 2 equals 0. The eigenvalues are lambda 1 equals 3 and lambda 2 equals 2. Lambda 1 equals 3. The matrix stretches vectors in this eigenspace by a factor of 3. Lambda 2 equals 2. It stretches by 2. Every subsequent calculation, finding eigenvectors, diagonalizing, depends on these two values. Once we have an eigenvalue lambda, we find its eigenvectors. By solving the homogeneous linear system A minus lambda I times V equals 0. This system has non-trivial solutions by construction. We chose lambda to make a minus lambda I singular. The method: substitute lambda into a minus lambda I, row reduce to row echelon form, identify the free variables, and write the general solution in terms of those free variables. Each free variable corresponds to one basis vector for the eigenspace. The number of free variables equals the geometric multiplicity of the eigenvalue. Important: the eigenvectors are not unique. Any non-zero scalar multiple of an eigenvector is also a valid eigenvector with the same eigenvalue. We typically choose the simplest form, often setting the free variable to 1. Never use the zero vector as an eigenvector, even if row reduction seems to allow it. That would indicate an error in the eigenvalue step. Back to our matrix A with eigenvalue lambda 1 equals 3. Substitute. A minus 3I has first row 0, 1 and second row 0, negative 1. We need to solve this matrix times V equals 0. The two rows are negatives of each other, so we have one independent equation. V sub 2 equals 0. The variable V sub 1 is free. Let V sub 1 equal 1. Then V sub 2 equals 0. The eigenvector for lambda 1 equals 3 is the vector with components 1, 0. All scalar multiples of this vector are also eigenvectors for lambda 1. Geometrically, the eigenspace is the horizontal axis, the x-axis. For eigenvalue lambda 2 equals 2. A minus 2I has first row 1, 1 and second row 0, 0. One independent equation. V sub 1 plus V sub 2 equals 0. So V sub 1 equals negative V sub 2. Let V sub 2 equal 1. Then V sub 1 equals negative 1. The eigenvector for lambda 2 equals 2 is the vector with components negative 1, 1. Verify, multiply A times this vector. First entry. 3 times negative 1 plus 1 times 1 equals negative 2. Second entry. 0 times negative 1 plus 2 times 1 equals 2. Result: negative 2, 2, exactly 2 times the eigenvector. Confirmed. The algebraic multiplicity of an eigenvalue is its multiplicity as a root of the characteristic polynomial. If lambda minus 3 appears squared in the factored form, the algebraic multiplicity is 2. It tells you how many times the eigenvalue is counted as a root. But it does not tell you how many independent eigenvectors correspond to it. The geometric multiplicity is the dimension of the eigenspace, the number of linearly independent eigenvectors for that eigenvalue. Geometric multiplicity is always less than or equal to algebraic multiplicity. When they are equal for every eigenvalue, the matrix is diagonalizable. When any geometric multiplicity is strictly less, the matrix is defective and cannot be diagonalized. Example of a defective matrix: A equals 1, 1 in the first row and 0, 1 in the second row. The characteristic polynomial is lambda minus 1 squared, algebraic multiplicity 2. But the eigenspace has only one independent vector, 1, 0. Geometric multiplicity 1. Since 1 is less than 2, this matrix cannot be diagonalized. It is called a defective or non-diagonalizable matrix. A matrix A is diagonalizable if it can be written as A equals P times D times P inverse, where D is a diagonal matrix and P is invertible. The diagonal entries of D are the eigenvalues of A, and the columns of P are the corresponding eigenvectors in the same order. When can we diagonalize? If A has n distinct eigenvalues, it is always diagonalizable. Distinct eigenvalues guarantee n linearly independent eigenvectors. For repeated eigenvalues, diagonalizable if and only if geometric multiplicity. equals algebraic multiplicity for every repeated eigenvalue. To build P and D, Step 1. Find all eigenvalues from the characteristic equation. Step 2. For each eigenvalue, find a basis for its eigenspace. Step 3. Place the eigenvectors as columns of P matching order matters. Step 4. Place the eigenvalues in D as diagonal entries in the same order as the columns of P. The reward, A to the power k equals P times D to the k times P inverse. D to the k is trivial, just raise each diagonal entry to the k. Diagonalize A equals 3, 1, 0, 2. Eigenvalues, 3 and 2. Eigenvectors, 1, 0 for lambda equals 3, and negative 1, 1 for lambda equals 2. Build P by placing eigenvectors as columns. First column is 1, 0 and second column is negative 1, 1. Build D as the diagonal matrix with entries 3 and 2. Compute P inverse for the matrix P with first row 1, negative 1 and second row 0, 1. For a 2 by 2 matrix with entries A, B, C, D, the inverse is 1 over the determinant times D, negative B, negative C, A. The determinant of P is 1 times 1 minus negative 1 times 0, which equals 1. So P inverse equals the matrix with first row 1, 1 and second row 0, 1. Verify. Compute P times D times P inverse. First, D times P inverse. Row 1 of D is 3, 0. Multiply by P inverse. 3 times 1 plus 0 times 0 equals 3. And 3 times 1 plus 0 times 1 equals 3. So row 1 is 3, 3. Row 2 of D is 0, 2. Multiply 0, 2. Combined, dP inverse equals 3, 3, 0, 2. Now multiply P times this result. First row gives 3, 1. Second row gives 0, 2. This equals A. Diagonalization verified. The power formula in action. Compute A to the 10th power. A to the 10 equals P times D to the 10 times P inverse. D to the 10 has diagonal entries 3 to the 10th and 2 to the 10th. 3 to the 10th is 59,049. 2 to the 10th is 1,024. Without diagonalization, you would multiply A by itself 10 times. With it, one computation exact answer for any power. The spectral theorem applies to real symmetric matrices, matrices where A equals a transpose. Every real symmetric matrix has all real eigenvalues, and a complete set of mutually orthogonal eigenvectors. This is guaranteed by the spectral theorem, one of the most powerful results in linear algebra. For a symmetric matrix, the eigendecomposition takes the special form A equals Q lambda Q transpose, where Q is an orthogonal matrix, its columns are the unit-length orthogonal eigenvectors, and lambda is the diagonal matrix of eigenvalues. Because Q is orthogonal, Q inverse equals Q transpose. This makes computation faster and the geometry cleaner than the general case. The outer product form of the spectral decomposition. A equals the sum from I equals 1 to n of lambda sub I times Q sub I transpose. Each rank 1 term captures one eigenvalue and its corresponding direction. This is exactly what PCA computes on the covariance matrix of data. The top eigenvector captures the direction of maximum variance, and the corresponding eigenvalue tells you exactly how much variance is in that direction. Watch this generic vector U with components 1, 1. When we apply A to U, mapping it to O, the direction changes, the vector rotates significantly. This rotation and scaling is the generic behavior of matrix multiplication. Most vectors are not preserved in direction. Now watch eigenvector V1 with components 1, 0. Apply A, the result is 3, 0, exactly 3 times V1. Direction identical. Only length changed, by factor lambda equals 3. Now V2 with components negative 1, 1. Apply A, result is negative 2, 2. Factor 2. Same direction preserved. These invariant directions are the eigenvectors. The axes the matrix cannot rotate. Principal component analysis. Given a dataset, compute the covariance matrix sigma equals 1 over n times x transpose x. This matrix is symmetric, the spectral theorem applies. The eigenvectors of sigma are the principal components, directions of maximum variance. Eigenvalues quantify how much variance each direction captures. Project onto the top k eigenvectors to reduce dimensionality while preserving information. Google PageRank. Model the web as a directed graph and build a transition matrix M, where entry ij is the probability of following a link from page j to page I. The PageRank vector is the eigenvector of M with eigenvalue 1, the steady-state distribution of a random walk on the web. The most important pages have the largest components in this eigenvector. Quantum mechanics. Observable quantities are eigenvalues of Hermitian operators. When you measure energy or spin, you get an eigenvalue of the corresponding operator. Markov chains. The long-run stationary distribution is the dominant eigenvector. Stability analysis. A dynamical system is stable if all eigenvalues of its matrix have negative real parts, unstable if any eigenvalue has positive real part. Eigenvalues govern whether systems grow, oscillate, or decay. Here is the complete framework. Eigenvalue equation. A v equals lambda v. Characteristic equation. Determinant of a minus lambda I equals 0 gives all eigenvalues. Finding eigenvectors. Solve a minus lambda I times v equals 0 by row reduction. Eigenspace for lambda, the null space of a minus lambda I, a spectral decomposition for symmetric A equals q lambda q transpose, q orthogonal. Outer product form. A is the sum of lambda sub I times q sub I transpose. Power formula. A to the n equals p times d to the n times p inverse. Applications. PCA uses eigenvectors of the covariance matrix. PageRank is the dominant eigenvector of the web transition matrix. Quantum observables are eigenvalues. Stability is determined by eigenvalue signs. These are not separate uses, they are the same mathematics powering the world. Next lecture. Singular value decomposition. The generalization of eigendecomposition to any matrix, not just square symmetric ones. Subscribe. I will see you there.